this video, we're going to look at the central difference method, and specifically the problem will relate to calculating velocity. So we're going to state what the central difference method is or how we use it. We're going to use it to solve an example problem. So calculate the velocity for frames 3 and 4 using the central difference method. So frames 3 and 4 are the frames 3 and 4 in this table. So essentially the information we've been given is on the motion of some particle or some moving body. We don't know exactly what it did, we don't know its position at any given time, but every so often information was recorded, so we sort of took a snapshot of what had happened at that time. So only at certain points, and these points are called frames. So at frame 2, when the time was 0.0167 seconds, we know that the position was 0.15 meters. Then at frame 3, the time had moved on and the position had changed, and so on at frame 4 and at frame 5. So we only have these discrete bits of information, these discrete recordings that were made at certain points, which we're calling frames. So this is the kind of information you might get from an experiment where you only take recordings every so often. So we want to use the central difference method to find the velocity. So you can see our velocity column is blank. We want to find it for frames 3 and 4. How do we do that? Well, we use this key fact that velocity equals change in position over change in time. So that's just generally true. That's the general definition of velocity, is it's how much did the position of the moving thing change over a given time. So if you think of when you do problems in school, you do speed equals distance over time. So you draw a triangle, speed, distance, time triangle. So that's sort of what we're using here, that velocity or speed is the difference in position over the difference in time. But when using the central difference method specifically, what we have to do is we use the information in the frame before the frame we're concerned about and the frame after. So we say, if you look at our table in frame 3, well, if we look at the time at frame 2 and the time at frame 4 and calculate the difference, and then we look at the position in frame 2 and the position in frame 4 and calculate the difference, we then just plug into this formula. So if you like, the central difference method is these two bits of information taken together, that we have to look at the frame before and the frame after, and then use the change in position from the frame before to the frame after and the change in time from the frame before to the frame after. Hence why it's called the central difference method, because then frame 3 is in the center in between 2 and 4. And we're calculating the difference between 2 and 4 in terms of time and position. So let's just try and do that. So we'll start with frame 3. So it's actually not so bad. Let's look at frame 3. Well, we're concerned with the times of frames 4 and 2. So these two times here, and also the positions. So these two positions here. And we just plug them into the equation. So we have change in position, so we have to subtract the old position, the position from frame 2, from the position in frame 4, and then the change in time, so we subtract the time in frame 2 from the time in frame 4. So we get 0.27 minus 0.15, so that's the change in position, divided by 0.0501 minus 0.0167, that's the change in time. Calculate this, we get 0.12 over 0.0334, which is roughly equal to 3.59. So let's put that on our table. And it's that simple really, that the velocity frame 3 from the central difference method was 3.59 meters per second. And then we just do the exact same thing for frame 4. So look at frame 4, we care about the information in frame 5, so the times and the positions. Plug them into the equation again, so we get change in position is 0.3 minus 0.22, and the change in time is 0.0668 minus 0.0334. Now you always subtract the one from the frame before from the one from the frame after, because you want the change, even if, so the time will always have increased, because time always increases of course. The position, depending on what the particle did relative to the origin in your experiment, it might have decreased because the particle might have moved closer to the point of origin where it started. And so you may end up getting a negative, but that's fine because velocity can be negative depending on the direction the thing is moving in. In this case that hasn't happened though. We end up with 0.08 over 0.0334. Put this into a calculator and you get roughly 2.40. So I'm rounding these two numbers to 2 decimal places. So I put that onto my table. I get that the velocity for frame 4 is 2.40. And that is how we use the central difference method to find velocity.